Okay, so in the last talk, I talked about linear algebra. I talked about classical mechanics. And in this talk, I'll talk about quantum mechanics. And there's a very deep relation. So if you understood the previous talk, hopefully you can understand this one. And if you showed up late, then I don't know how you'll do. So I give this phase space picture in classical mechanics, where you can represent a mechanical system in terms of how it transforms position and momentum. And I said that the maximally compatible, affinely constrained configurations of the system, of things flowing through the system, is represented by affine Lagrangian subspaces, which can be composed by a relational composition. And here I'll talk about how this kind of formalism can be quantized so that nicely behaved fragments of quantum mechanics admit the same kind of non-deterministic semantics in terms of these affine Lagrangian relations. So there's two kinds of versions of this. The first quantized fragment of classical mechanics is finite dimensional, and it's called stabilizer quantum mechanics, where the position is like given by the Pauli observable and the Pauli Z observable, and the momentum is given by the Pauli X observable. And the second version is like a continuous variable, infinite dimensional kind of version of this, which is called Gaussian quantum mechanics, which the name will become evident in a few moments. So first, I'll talk about the finite dimensional thing, because infinite dimensional quantum mechanics is kind of a bit tricky. So from the point of view of like a category theorist who doesn't know anything about quantum mechanics, I would say that finite dimensional quantum mechanics is just the category of finite dimensional vector spaces with respect to the bilinear tensor product as the monoidal product. And this isn't a prop, because there's different types of wires of different dimensions. So what people will do is they'll fix some number p, which I'll require to be a prime number for convenience, and they'll look at the vector space of dimension p, and they'll give this should be p. They'll give an order to basis elements. So you have d basis elements starting from 0 and ending at d minus 1. And the Pauli group is a subgroup of the unitaries of dimensions p to the n, and it's generated under the bilinear tensor product and composition by these two operators. The x operator shifts the basis element, and then the z operator kind of rotates around the complex unit circle by increments of p, so by primitive root of unity of order p. And together this forms the Pauli group. And what's really nice about the Pauli group is because you can always commute these z and x operators up to a phase in this form, and you can represent every element of the Pauli group as follows. So you take some shift around the complex circle A, and then you just have these vectors z and x, which on different wires give you different positions, different momentums. So in stabilizer quantum mechanics, what's really useful to do is to not actually work in vector spaces itself, but to work in terms of these subgroups. So if you have a maximal abelian subgroup of the Pauli group, then this uniquely determines a normalized state such that for every element in the subgroup, it's a +1 eigenvector of this state. And these are called stabilizer states. And because this subgroup is required to be abelian, we care about when these things commute. And two Pauli operators commute when their symplectic form values to 0. Let's just say they're compatible in this sense, which I gave earlier. And there's this nice result by Gross, which says that these maximal abelian subgroups of the Pauli group are in bijection with these affine Lagrangian subspaces, now over a finite field instead of the real numbers. And this is in bijection with these stabilizer states. So these are all the same thing in a sense. And the Pauli Z powers are these kind of abstract positions. The Pauli X powers are these abstract momentums. And this A thing on the complex circle is determined by the affine shift. So because finite dimensional vector spaces under the bilinear tensor product is compact closed, we can get a prop of stabilizer circuits. So generated by stabilizer states from 0 to n. And then the caps coming from the complex those structures. So we can kind of bend some of the output waters into input waters and so on. And I'll call this the prop of stabilizer circuits. And Alex and I showed that the relational composition of these subspaces agrees with matrix multiplication, so that affine Lagrangian relations over, this should be FP, is isomorphic to these Cupid stabilizer circuits modulo scalars. And what's really nice, and which really helped us with our proof for the completeness of these affine Lagrangian relations, is that up to scalars, these affine Lagrangian relations over FP is isomorphic to what's called the Cupid stabilizer ZX calculus, which was a paper by my co-authors and probably lots of people in this room. Yeah. And stabilizer quantum mechanics is powerful enough to do at least finite dimensional quantum teleportation. So I've just kind of copied this from the Dodo book of this proof. But this is still a diagram in affine Lagrangian relations if you want. And the idea is Alice wants to teleport this channel to Bob, and they share a Bell state. They perform an entangling operation, a control knot gate, and then Alice performs a Bell measurement where she measures the position Z and momentum B, sends it classically to Bob, which he uses to perform a correction on the quantum channel. So that beforehand they share this quantum state and they only have to send classical information. And then just using the equational theory, which I provided, you can simplify things to get the identity, which means that without any error, they can transmit the quantum state to each other. And they only need stabilizer stuff. They don't need more complicated quantum operations at all. Okay, so that's the end of the finite dimensional picture. So hopefully that was well understood, because infinite dimensions, things get a lot more hairy. So that in finite dimensions, the state space is given by a prime dimensional vector space, but in continuous variables in infinite dimensions, it's a bit more tricky. So now a single wire, as it were, corresponds to the Hilbert space of square integrable functions on the real numbers. So now the Hilbert space itself is composed of functions such that if you take any function in this Hilbert space and you take the integral, evaluate it at over the real numbers, and you take the absolute value squared, then this is finite. And now, like the allowable morphisms between these things are bounded linear maps. So if you have n wires coming in and m wires going out, then you can't just ask that you have a linear map. It has to be bounded. Otherwise the analysis goes crazy and things don't make any physical sense. And there is continuous variable generalizations of the Pauli operators. These displacement operators, what they do is the continuous variable Pauli Z operator, it rotates now along the complex circle, but by any real number, not just by a primitive root of unity. And the Pauli X operator, the momentum operator, what it does is it shifts the argument of the function it's being applied to. And together, these operators under the tensor product and composition form a group, which is sometimes called the Heisenberg-Weyl group. And it has the same kind of properties as the Pauli group. So every element has this form where you have some A, which determines how much you go around the complex circle. And then the Z and X determine the positions and momentums on each of your wires. And you can do the same thing. You can say, well, I can compose these things as affine Lagrangian relations, right? So an affine Lagrangian subspace over the real numbers is in bijection with these maximal abelian subgroups of the Heisenberg-Weyl group up to scalars. But there is a problem, a really big problem, in fact, that if you take some affine Lagrangian subgroup over, it should be Rn, the symplectic vector space of dimension 2 to the n, with the symplectic form omega n. then there is no version of the stabilizer state. There is no bounded linear operator such that for every element of the group, it's a +1 eigenvector. So this is a massive problem because it means that if we were to regard affine Lagrangian relations over the real numbers as sort of an infinite dimensional generalization of the stabilizer ZX calculus, that means that there's no states that have any physical meaning. So we have part of this correspondence, but the Hilbert space kind of picture doesn't make any sense, only the phase space picture. But luckily there is a solution. So recall that a Gaussian distribution is determined by a positive semi-definite covariance matrix and a mean. So like for dimension 1, where you just have the real line, and say this is 0, and this is your mu. You have a Gaussian distribution, and then the mu is like the peak of the Gaussian, and the covariance is like determines the spread. But in higher dimensions, you need the mean is now a vector because you can move the peak of the distribution around on a higher dimensional space, and the covariance is this positive semi-definite matrix. And it turns out that if you have a 2n variate Gaussian probability distribution on the phase space, that this faithfully corresponds to a bounded space on n continuous variable modes, if and only if, first of all, the covariance matrix is strictly positive definite, which means that the Gaussian distribution has a density. And second of all, you require these two conditions, which correspond to the distribution obeying Heisenberg's uncertainty principle for pure state quantum mechanics. And I'll get back to this to give some sort of intuition of what this means, but I'll call these kinds of Gaussian distributions, which correspond to these quantum states, quantum Gaussian distributions. So this is the kind of the phase space version of a stabilizer states, but in continuous variables. You take some Gaussian instead of just a subspace, because the subspace is not bounded. So you kind of have to like take a distribution which makes things smooth, and in turn makes the state bounded in the Hilbert space picture. So the most important quantum Gaussian state is called the vacuum state. And on a single continuous variable mode, this is represented by a Gaussian distribution of this form. So the covariance is just the identity matrix, and there's no affine shift, it's just at the origin. So this is like, it has kind of a unidal spread, and it's uniform in all directions, and it's going through the origin. So in fact, this is the unique quantum Gaussian distribution on a single quantum mode that is invariant under rotation. And in higher dimensions, if you take the tensor product of this thing in phase space, this is the same quantum Gaussian state, which has the property of being uniquely invariant under these symplectic rotations, which I won't get into, but formally it's you take the group of rotations of dimension 2n and you intersect this with the symplectic group. And I didn't mention this earlier, but in this category of affine Lagrangian relations, all of the automorphisms have this following form. So they're the affine transformations which preserve the symplectic form. And in particular, all of the quantum Gaussian states can be obtained by acting on this vacuum state, which I described on the previous slide, by these affine symplectomorphisms. So from a geometric point of view, this means that you take this kind of uniform distribution of a dimension 2 with the uniform spread or unidal spread. You take the tensor product and then you apply transformations which locally preserve the area on the plane. So to give one-dimensional examples, because in higher dimensions I have no way of visualizing this, you take the Gaussian distribution on the vacuum state and you can squeeze it, because this transformation preserves the area. So if you want to squeeze out the momentum, then the position has to get thinner, because otherwise it wouldn't preserve the momentum. And you can do other things like take this guy, which now is a valid quantum Gaussian distribution, and you can shift the mean and rotate it to get something like this, and this is still fine. But you can't do things like this because this would violate the Heisenberg's uncertainty principle. You can't take your Gaussian distribution and just make it really, really concentrated at the origin, because then you could have more definite knowledge of position and momentum simultaneously, which is not allowed. And in fact, the software which I used to render these diagrams wouldn't allow me to create this thing, so I needed to go into GIMP to stretch it out because it's not allowed. And there's like, you can see artifacts of stuff there. Yeah, so you can approximate continuous variable stabilizer states, which I said are not valid things in spaces, by taking your Dirac delta distribution, which is just, you can visualize as a line in phase space, applying convolution, but convolution that respects the uncertainty principle, so that, say, in the position, you want to make it thinner, and in the momentum, it gets very wide. So then you'll get things like this, which are actual Gaussians with density, instead of this thing, which has no density. And yeah, we also have a complete equational theory for this fragment of quantum mechanics. And what you do is you take this affine Lagrangian relations over the real numbers, and you add a single generator. And you want to impose on this generator that it's the unique thing which is invariant at a rotation. So recall on a single wire, this corresponds to a two-dimensional real vector space. And what we've done is we've just taken a rotation with angle theta, and we've decomposed it into 3 shearing operations. And we're saying that this should be preserved, so this can be co-discarded. And similarly, this is if you have a rotation if you have a rotation on two dimensions, and you take this embedding, which I've described, which is doubling, which comes from the cotangent bundle, then this is also invariant. So in fact, these two things generate the symplectic rotations. And this other equation on the left is just saying it's still a category of relations, so there should be no scalars other than the empty set and the identity. So the kind of all of the stuff which is in Af by Garel, this is the CV stabilizer picture, and then adding this, you also get Gaussians. So this is like a more richer notion than just the Gaussian fragment. And we have also semantics using the complex numbers. So a quantum Gaussian state or a union with the CV stabilizer states can be represented by certain affine Lagrangian subspaces over the complex numbers then, where we ask that the affine shift is real, because the idea is that the displacement of the Gaussian distribution still has to lie on the real plane. But now we ask that for any vector in this thing, if you take the complex number I and you evaluate it on the symplectic form where one of the sides is conjugated, that this is strictly greater than 0. So this is a weird condition, but in terms of the string diagrams, it's really simple. All we're saying is that you take your affine Lagrangian relations over the real numbers, you embed this into affine Lagrangian relations over the complex numbers, and you just add a single complex generator, which is the state which has 0 displacement, and you take a shear by the complex number I. So this what I described earlier, which is an approximation of a Dirac delta distributions, can now be given in terms of our equational theory. So you have on the left this Dirac delta thing, which is not a valid state in Hilbert spaces, and you can apply this convolution, which is this string diagram, and when you compose them together, now you get this guy. So this epsilon determines how squeezed it is in this dimension, and I is needed to make it Gaussian instead of have density. And what's also really nice is that for the first time ever that I'm aware of, now we can give a graphical proof of the continuous variable quantum teleportation algorithm. So recall, for stabilizer states, things were really simple. It's just this wire bending operation. But in particular, in infinite dimensional quantum mechanics, it's not compact closed, so there's no cup. So what you have to do is you have to take like an approximate, you have to take the cup and apply Gaussian convolution to get some approximate cup. You do all of the same kind of business and you simplify it, and what you get is not the identity channel, but you have a channel which is the identity up to some Gaussian noise factor. That's it.
Any questions? Yeah. You probably notice like the spectrum a long time you can see that the city down in the latency and normalization
Yeah, so Speckens and the co-authors have done similar things. First for the finite dimensional case, and later they had something for Gaussian quantum mechanics. And it's essentially the same story, but they don't give they're not category theorists. So what they do is they separate things into three stages. They first start with states, and they act on the states with isomorphisms, and then they measure the things using measurements. So they have this kind of physicist's perspective of every computation. The measurements, the evolution, and the preparation are all distinct things. So if you combine them all together, then this is the same thing, essentially. Yeah, so if you take affine Lagrangian relations over the field, the finite field of order 2, the prime field of order 2, this is precisely Miriam's calculus.
Yes.
About that, what you were saying right now, so I guess measurements are not really featured in this story so much. What is it of the how do they think in the story, or is it something that
yeah, homodyne measurements nicely fit in the story, but we wrote the paper for a 15-page limit, so we didn't include it. But if you relax this compatibility requirement so that the subspaces are not maximally compatible but merely compatible, then you get this this category of affine coisotropic relations, which works really nicely, where you kind of add the quantum trace, and then if you split the projectors like in the style of Selinger, then you have like that measurements. This would be like a Z measurement. It takes your position momentum and just discards the momentum and then allows the position to pass through. And there's a nice equational theory, but we just didn't have enough space to put it in the paper.
we need that thing?
No, but now you'll just have two types of wire. You'll have like a classical wire and a quantum wire. But
Ready double.
yeah, exactly.
Further questions? Yes.
So you said the problem with it have these stabilizer subgroups in narrow state.
Mhm.
That's is in some sense that these Gaussians are like approximating that state. What's the connection there?
So from a physicist point of view, if it's like they think of these stabilizers as like real things, but that they can never be actually achieved. So if you just put more and more energy or more and more time into trying to get the stabilizer state, you'll just get a Gaussian state, which is more and more, which resembles more and more the infinitely squeezed thing. So yeah, it really is just an approximation.
Yeah, does that correspond to something that like if I take that very squeezed state, apply this operator to it, which is very clearly my state.
Yeah, it's like an eigenstate with up to some probability or yeah.
That's it. Thanks again.